Okay, hello and welcome to part 2 of this video, which is going through the AS mechanics paper, the June 2013 one. Okay, so moving on to question 2. It says explain why force is a vector quantity. You want to say because it has a direction. Okay, you must spell the word direction correctly to get the mark there. Okay, so if you remember from class, vectors have magnitude and direction. Whereas scalars, okay, just write that down, scalars only have a magnitude. So for our example, the force, if you just imagine that you've got a block on some kind of surface or something, and you apply a force of 10 newtons in this direction, you'd say the magnitude is 10 and the direction is to the right. Okay, some things don't have a direction, and we just said that they're called scalars. There are a list of scalars and vectors in your textbook, which I recommend you learn. Okay, but you can always try, in most instances, if you do forget, to just apply the common sense approach. Does it make sense to give it a direction? Or does it make sense to give force a direction? Yes, definitely it makes sense that you can apply a force to the left, right, up or down, or whatever. But if you have something, say, like energy, so let's say we have 10 joules of energy, does that make sense to talk about 10 joules of energy to the right? Well, no, it doesn't make sense to give energy a direction, and energy is a scalar. Okay, so moving on to the next question. Figure 2.1 shows the forces acting on a water drop on the windscreen of a stationary car. The windscreen makes an angle of 30 degrees to the horizontal. The weight of the water drop is 8 times 10 to the minus 5 newtons. The normal contact force on the water drop is R. That's this one here. Let's just remind ourselves what a normal contact force is. If you have a surface like a table, let's say we have something like a book on the table. Okay, that's not drawn very well. Let me just draw that again. Okay, you've got a book on the table. There's going to be a downward weight force. Okay, but the table, or the surface of the table, will produce this equal and opposite normal contact reaction force. Okay, that stops the book falling through the table. So it's the equal and opposite force that the surface exerts on objects to stop them falling through the surface. Okay, and it's always perpendicular. The reaction force R. It's always perpendicular to the surface. So you can see, because we're on an incline here, you can definitely see that this reaction force is perpendicular to the surface, and it's stopping the raindrop going through the surface. Okay, it says there's also a force F acting on the water drop as shown. It's this one here. And it says the water drop is stationary. That's an important point, because that tells you that the overall net force is 0. So all these forces cancel each other out. Okay, it says use the figure to determine the component of the weight of the water drop. It's this here. Perpendicular to the windscreen, first of all. So the perpendicular component. How do we do that? Well, force is a vector, as we just discussed, so it can be broken down into components. If you remember from class, that just essentially involves making a right-angled triangle. And it's very important you do this the correct way. In this example, this downward weight force is the overall force. So it must be the hypotenuse of your right-angled triangle when you're breaking this vector into components. Okay, so for example, you wouldn't go about it like this, because then it's not the hypotenuse, whereas it must be, because it is the overall component in this example. So let me just see if I can find an arrow to try and show these quite clearly, and I'll try and make them different colours. So let me just turn this into a right angle triangle, and I'll choose blue. Okay, you can now see that I've turned this into a right angle triangle. How do I know that this arrow points down the slope? Well, we know that the weight of an object is what causes it to go down the slope. So this direction must be down the slope. And you connect vectors tip to tail. And you can see I've done that. So I've connected the tail of the blue vector to the tip of the red vector. And that's how you connect vectors. And you can see that the red one plus the blue one gives us overall downward weight force. Okay. So what we've got to do now is we're going to work out the perpendicular component. This involves using trigonometry. So if we write the trigonometry equation, so sine of the angle equals opposite over hypotenuse, and then you've also got the cosine of the angle equals the adjacent over the hypotenuse. Before we start doing that though, we need an angle inside our right angle triangle that we've made, which we don't have yet. There's lots of different ways of going about doing this, but this is quite straightforward, where if I make this into a triangle, a right angle triangle, I know this is 30 degrees, it gives me this in the question, therefore this must be 60. But this angle I've just found is part of the original triangle we made, so I know that that's 60 now. If that's 90, that's 60, this is 30 degrees. Okay, and that's the one I'm going to use because I like using the one that they give you in the question, so I didn't want to do that. Okay, so let's use this one. So this is 30 degrees. Okay, so the perpendicular component is this blue leg, or that blue component is adjacent to this angle. You can see it's adjacent to the angle, therefore I'm going to use the cosine. So I'm trying to find the adjacent, that's what I'm trying to find. So adjacent equals the cosine of the angle, okay, times the hypotenuse, okay, and therefore adjacent equals cosine 30 times the hypotenuse, which is 8 times 10 to the minus 5. Okay, if you plug that into your calculator, you'll get 6.9 times 10 to the minus 5. So 6.9 times 10 to the minus 5 newtons. Okay, so if we move on to the next part, it says now we have to calculate the parallel component to the windscreen. Okay, well the parallel component is going to be this red vector here. Okay, you can see that this red vector, or this red component here, is opposite the 30 degrees. So we're going to use the sine, and obviously we're finding the opposite because that's what the red component is. So therefore we're going to get that the opposite, and I'm going to do it all in one step this time. Opposite equals the sine of the angle, which is 30, times the hypotenuse, which is 8 times 10 to the minus 5. Okay, if you plug that into your calculator, you'll get 4 times 10 to the minus 5 newtons. So this opposite equals 4 times 10 to the minus 5 newtons. Okay, so we've done it now. We've worked out the perpendicular component to the windscreen. That's this blue one, 6.9 times 10 to the minus 5. And now we've worked out the one that's parallel, which is 4 times 10 to the minus 5. Just be very careful, make sure whenever you break a vector into its components, always make sure that the resultant vector, the overall vector, is your hypotenuse. Okay, so just moving on to the next question. It says determine the magnitude of f, explain your answer. So if we just go back, it's saying determine the magnitude of f. Well, this is where this becomes very important, that the object, or the water drop is stationary. That means all the net forces on it are 0. So if we've worked out this red component here that's trying to drive it down, which is a component of the weight force that's trying to drive it down the slope, if we know that's 4 times 10 to the minus 5, then F must also be 4 times 10 to the minus 5 to give an overall net force of 0, because it's stationary. Okay, so if we go back to this one, we can write that F equals 4 times 10 to the minus 5 newtons. Okay, that will score us 1 mark. Second mark is just for saying why, so you can say something along the lines of I'll put the net force parallel to the windscreen. Okay, the net force parallel to the windscreen is 0. That's why we knew we could determine what this one was, and that was given to us in the question when it said the water drop was stationary. Okay, so I'm just going to stop this video over here, and I'll continue the rest of it in part 3.